Alrighty, physics fam. So today we are looking at blocks and strings and inclined planes and pulleys, and we're just going through 4 scenarios, which are really super common scenarios, but students often find quite tricky. But really, it just comes down to how do you set out your working. If you set out your working, then in pretty much every single question's all the same. We just got to look at what forces are assisting the motion of the system, and which force or forces are resisting the motion of the system. Alright, so we start with this scenario. We've got, you can see there's 2 blocks. We've got a 5 kilo block and we have a 10 kilo block. You can see I've just labeled them as object 1 and object 2. Okay, and you can see that they're linked by some string, which is under some tension T1. And there is also a 50 Newton force being applied to the 5 kilo object. And it's asking us just to find acceleration. Okay, so when it's asking us to find acceleration, we need to understand, firstly, it's talking about the acceleration of the entire system. All right, so we can kind of treat this system as the 10 kilo, 5 kilo block system. All right, so we start off with just by saying the net force is just the assistive forces minus the resistive forces. So the forces that are encouraging the motion of the system and the forces that are resisting the motion of the system. So you see in this scenario, there is one force kind of causing that system to move forward. So that is our force of 50 newtons. And you can see that there are no resistive forces. So there's no mention of any friction or any, I don't know, air resistance or anything like that. So it's really just us saying the assistive force is 50 and the resistive force is 0. Okay, so we know our net force is just going to be m times a, so we end up with ma is equal to 50 minus 0. Really important to recognize that this m, because we're looking at the entire system, this m is actually the sum of the masses of the objects in the system. So our m is going to be 10 plus 5. Our m is going to be 15 kilos. Right, so we end up with ma is going to be 50, so therefore our a is going to be 50 over 15, okay, which gives us 3.3 ms to the minus 2. Okay, we've got enough information to tell the marker, then I know that it's moving towards the right. Okay, so we've got 3.3 ms to the minus 2 towards the right as our acceleration for the system. And then it's saying find tension in the string, which is labeled as T1. So usually, I mean, there's a couple of different ways of doing it. So firstly, let's consider, we've got our object number 1. So we'll call it Fnet1. So I want to come up with an expression for the net force which is acting on object 1. And once again, it's the same thing. It's the forces assisting its motion minus the forces that are resisting its motion. So the assistive forces here is just the 50 newtons. And when you look at it, are there any resistive forces? Well, there actually is. Remember, tension's that weird force. According to the 10 kilo force or the 10 kilo mass, tension's acting towards the right because it always acts away from the object. Whereas according to the 5 kilo object, tension's actually acting towards the left. So again, away from the object along the string. So we end up with our expression for the net force on object 1 is actually 50 minus T1. So 50 minus T1 is our net force on object 1. We can also do the same thing for the net force on object 2, Fnet2. Now here, the force which is assisting its motion is T1 again. Again, T1's acting along the string, always away from the mass. So therefore it's acting towards the right. So we've got T1, which is assisting its motion. Now resisting its motion, again, there's nothing acting towards the left on the 10 kilo mass. So therefore it's just T1 minus 0. All right, so we end up with, let's have a look at this first one. So we can rearrange this for T1. So T1 becomes 50 minus the net force on object 1. The net force on object 1 is just the mass of object 1 times the acceleration experienced by object 1. So that is 5 times 3.3. Okay, now that comes out to be around about 33.3 newtons. Now, we have solved, therefore, for the mass, for the tension in string 1. But sometimes, I mean, you want to kind of, make sure that you are correct and kind of confirm our answer. So here we can say, well, T1 is going to be M2A. Now, this should also be 33.3. We've got a 10 kilo mass and an acceleration of 3.3. So that gives us 33.3 newtons. Okay, so 33.3 newtons is going to be our tension in that string. All right, so let's move on to the next one. So next one we have scenario 2. We've got block sliding horizontally linked by a string with a pulley, and it's asking us to find the acceleration, again, of the system. So when we'll write it out, we'll just simply say our Fnet is going to be our assistive force minus our resistive force. Okay, now when you consider for the entire system, what is causing it to move, or what is assisting its motion, is just simply the weight force of this 7 kilo mass. Now, resisting its motion, again, there's no mention of any friction or any resistive forces or anything like that. So it's simply just going to be 7 times 9.8, okay, which is 68.6 newtons. So 68.6 newtons, that is our net force, which is acting on the system. Okay, again, keep in mind, this is the entire system. So when we work out the acceleration, we say acceleration is Fnet over m. So it's also going to be the mass of the entire system, which if you have a look at it, so it's 7 plus 5 plus 10, which is going to give us 22. And that'll give us an acceleration of about 3.12 ms to the minus 2. And that's our final answer. All right, so 3.12 ms to the minus 2 is our acceleration of the entire system. Now, keeping in mind, because everything's kind of nice and rigid, so if it's 3.12 ms to the minus 2 for the entire system, then it's 3.12 ms to the minus 2 for every single object inside the system as well. Okay, so this is telling us that the 7 kilo mass is accelerating at 3.12 ms to the minus 2, the 5 kilos accelerating at 3.12 ms to the minus 2, and the 10 kilos accelerating at 3.12 ms to the minus 2. Okay, now it might be accelerating in different directions because we've got this little pulley thing here, which is changing the direction of the force, but the magnitude of the acceleration is always the same for every single object, which is inside this completely rigid system. All right, so then we've got to find T1, T2, and T3. One thing to firstly note before we even start to solve for anything is that the string which is connecting the 7 kilo and the 5 kilo, you notice that it's one single string. Okay, now we're going to make an assumption. In this case, we're going to ignore any kind of frictional losses within the pulley itself. And we're going to say, because it's one string and the tension in the string is uniform, T1 and T2 are actually going to end up being the exact same thing. Okay, so they're going to be the exact same magnitude of tension. So we only really need to solve for two tensions here. So it's either T1 or T2 and also T3. Okay, so let's have a look again. Object 1, I've labeled everything. This is one thing you really need to get into the good habits of with your marker. You know, I've labeled this object 1, object 2, object 3. You know, I've labeled this as T1, T2, T3. Get into good habits labeling things for the markers just to make it easy. All right, so here we have our net force for object 1. So let's call it Fnet1. Now, forces, which is kind of, you know, assisting the motion of the 7 kilo, is going to be the weight force down. So we'll just call that M1G. And then what force or forces is resisting the motion of that 7 kilo mass downwards? We've got our tension T1. So it's M1G minus T1. Okay, so our net force there, we know it's going to be mass times acceleration. So it's 7 times 3.12, that is our MA. And that is going to be 7 times 9.8 minus T1. Okay, so from this we can just rearrange and solve for T1. T1 ends up being about 46.8 newtons. Okay, thereabouts. And then again, we're just going to say, well, T1 is equal to T2 because it's the same string and tension is uniform. Therefore, T2 is also going to be 46.8 newtons. I don't know why I just drew a 4 there. T2 is also 46.8 newtons. Nice. Okay, but at least give a reason. Say, you know, T1 is equal to T2 as it's like a common string or something like that. Okay, and tension is uniform throughout the entire string. I'm just going to move this acceleration bit up a little bit. Whoosh. Cool. And then we're going to solve for T3. All right, so to solve for T3, we're just going to say the net force acting on object 3. So if we just look at object 3 over here. Okay, over here we've got our 10 kilo mass. You can see that there's one force assisting its motion, that is force T3. And there's no force or forces resisting its motion. Again, there's no friction, no nothing like that. So we just say that the net force acting on object 3, it actually just is legit T3. Now our net force is mass times acceleration, so it's 10 times 3.12. Therefore, T3 is 31.2 newtons. Okay, so the tension in T3 is 31.2 newtons. All right, on to the next one. Okay, next scenario, we have blocks sliding up a ramp, no friction with a pulley, and again, it's asking us to find acceleration. So a little bit different now because it's not just a nice flat kind of horizontal surface. We've now got an incline, and what that means is we're going to have a component of the object's weight force acting parallel to the ramp, and a component of the object's weight force acting perpendicular to the ramp. All right, so that's one of the things that you guys should become familiar with. That is, we go to our center of mass kind of thing. We'll draw our mg, our weight vector downwards, mg, and then we'll break that up into two perpendicular bits. So remember, it doesn't matter what the perpendicular bits are as long as they're perpendicular. Okay, so we're just going to define the two perpendicular bits as parallel to the ramp and perpendicular to the ramp. Okay, and why we're doing that is because we've got to recognize that the stuff that's parallel to the ramp is going to cause the acceleration up or down the ramp. Okay, and then we've got this perpendicular bit here, which is going to relate back to the normal force, which doesn't really have too much of a role in this particular question because there is no friction, but in the next question, it is going to have a bit of a role in the determination of friction. Okay, so this is going to be the same theta as down here, which we can prove. Okay, but this is going to be mg sine theta, and this is going to be mg cos theta. We only care about the mg sine theta for this particular question. So let's find that acceleration. Okay, so our acceleration of the system is force or forces assisting its motion. Okay, which in this case, if I let this go, what would you expect? You'd expect the heavy one, the 10 kilo mass to fall downwards, and you'd be expecting the 5 kilo mass to slide upwards. So therefore, the force or forces assisting its motion is the one that's causing the 10 kilo force to fall. So we'll say here F net, douche, once again is F assisting minus F resisting, and F assisting is going to be 10 times 9.8. Okay, so once again, there's no mention of any kind of friction or anything like that. So the only force which is resisting its motion in the system as a whole is going to be the mg sine theta. Okay, so this is going to be, let's actually put in the numbers. So the mass of the 5 kilo object, so 5 times g of 9.8 times sine 25. Okay, this is then going to give us around about 77.3 newtons. So 77.3 newtons is going to be the net force, which is acting on the entire system. So we'd therefore say, well, acceleration is just net force divided by mass. Okay, once again, it's mass of the entire system because we just found the net force on the entire system. So it's 77.3 over 15, which is 5.15 ms to the minus 2. Okay, so 5.15 ms to the minus 2 is going to be the acceleration of the system as a whole. And then it is find T1 and find T2. Okay, so what do you notice about T1 and T2? So much like that previous question, it's the same common string. So we only really need to solve for one of those two values of tension because they're actually going to end up being the same. All right, so let's have a look at it from the 5 kilo object's perspective. So let's just call it F net. Let's just call it object 1. So call that object 1, object 2. So we've got F net 1 is going to be T1. So that's the force which is trying to drag it up the ramp. So the assistive force of T1 minus the resistive force here of mg sine theta. So T1 minus m1g sine theta. Now when we rearrange this, when we rearrange this to find the subject, so we want to try and make T1 the subject. So we get T1 is going to be m1a plus m1g sine theta. Okay, so once again, you've got all these values. So we've got 5 times 5.15 plus 5 times 9.8 sine 25. Okay, and when we solve for that, we get our T1 force of about 23.7 newtons. Okay, and keeping in mind that T1 and T2 are the same thing, well, therefore we get our tension force T1 is equal to our tension force T2, which is equal to 23.7 newtons. All right. Last question. Last question. So here it's a little bit different. Again, we've got blocks sliding up the ramp with friction, with pulley. So it's the exact same scenario as this one, with the exception of now there's friction. So you see without friction, there is 5.15 ms to the -2 of acceleration. But now acceleration is only 2.2 ms to the -2, and we need to find mu. Okay, so most importantly, once again, we kind of consider them object 1, object 2. Now let's think about it in terms of, what's the equation for the net force, which is acting on object 1, and what's the equation for the net force, which is acting on object 2. So we'll look at object 2 first because it's the easier one. So we would have weight force down, mg, and then we would have our tension force. Let's just call it T because, again, we recognize that the tension force is going to be the same through the string. So you've got mg and T. So the net force on object 2 is simply just going to be m2g minus T. Okay, so once again, it's the assistive force. It's the force trying to make the object move in its direction, m2g. And then it's the force trying to resist the object moving in that direction. So that's the tension force up. Let's do the same thing for the 5 kilo mass. Okay, let's call that Fnet1. So Fnet1 is going to be what force or forces are acting up the ramp. Okay, so we've got tension now acting up the ramp. What force or forces do we have acting down the ramp? So now we've actually got two forces acting down the ramp. There'll be m1g sine theta, and there's also going to be the frictional force. Now you see the question, it wants us to solve for the coefficient of friction. Well, then we better put in the expression for friction in terms of the coefficient of friction. That is, remember, friction is equal to mu times the normal force, or friction is fun. All right, so let's chuck that in. So we're going to have minus mu times the normal force. Okay, but this is inclined. And so remember, our normal force is actually just going to be mg cos theta. Okay, so it's mu times the normal force. The normal force is mg cos theta. So therefore it just becomes mu times mg cos theta. All right, so when we look through the actual question, so I should be able to determine what the net force is because I know the acceleration of the system. So I should be able to determine this. Now tension I can't determine just yet. Okay, but I know the values for all this stuff. I know the values for all this stuff. I don't have mu. So you're kind of like, oh, geez, do I need to go through the whole rigmarole of actually solving for tension? The quick answer is no, you don't, because you can actually just like sum these two forces. So Fnet1 plus Fnet2 is going to give us Fnet on the entire system. All right, so let's just say Fnet system is going to be Fnet1 plus Fnet2. The tensions are actually going to cancel. So when you look at it from a system point of view, there's really only one force trying to drive the system forwards, and that is the weight force of the 10 kilo. Okay, the m2g downwards. Okay, and then we're going to have some resistive forces acting on the 5 kilo, which is again part of the system. That's the parallel component of the weight force and the frictional force acting on the 5 kilo. Okay, do note, of course, the frictional force only acts on the 5 kilo mass because of the 5 kilo mass, which is sliding up the ramp. There's no friction acting on the 10 kilo mass, just simply because the 10 kilo mass isn't in contact with anything. Okay, it's just falling through air. Okay, we ignore like viscosity of air and stuff. Okay, so let me just chuck this over a little bit, give myself a little bit more room. Okay, and kind of go douche, douche, douche. So Fnet system is going to be m2g, okay, which is our assistive force, our force which is causing the system to move forward, then minus our resistive forces, so m1g sine theta minus mu times mg cos theta. And this is the fun part where we get to plug in some numbers. Luckily I have my trusty calculator with me. Fnet on the system, okay, is going to be, we got 10 plus 5, so 15 kilos multiplied by the acceleration of 2.2. Fnet on the system is 33 newtons. Okay, so 33 newtons, I'm not going to have enough room up there, so I'll chuck it down here. 33 newtons is going to be m2g, so that's 10 times 9.8, so 98. Minus m1g sine theta, so that's going to be minus 5 times 9.8 times sine 25. 5 times 9.8 times sine 25, which gives us 20.71. Okay, let's call that 20.71. And then we're also going to subtract mu times mg cos theta. So it's mu times 5 times 9.8 times cos 25. So 5 times 9.8 times cos 25. So that gives us about 44.41. So this becomes minus 44.41 mu. Now, I mean, pretty much here, now we've got our entire equation. So we have 33 is equal to 98 minus 20.71 is 77.25. Sorry, 77.29 minus 44.41 mu. All right, so when we rearrange this and we make mu the subject, so mu is going to end up being 77.29 minus 33 over 44.41 minus 44.41. So we end up with a mu of around about 0.998. There we go. Okay, now do keep in mind that coefficient of friction, what it is, it's a ratio of two forces, so therefore there are no units for coefficient of friction. Yeah, but there we go. So there's 4 quick scenarios involving strings and ramps and pulleys and masses and stuff. Hopefully that helps us out a little bit. Yeah, for our further studies. Cheers.